with Nathan, Camden, and myself, Brad. So a quick overview. What we're trying to do, we initially started our group on producing hydrogen, but storage for hydrogen is a rather complicated thing due to how small of a structure it is. So we decided to focus our efforts on creating methane, CH4, that can be later split into hydrogen for energy use later. So we're trying to synthesize methane from CO2 and H2O, and then have that methane ready for steam reformation into hydrogen when it's needed. So synthetic methane closes the carbon cycle, so there's no net carbon footprint because we capture the carbon to begin with before we release it back out into the atmosphere. And it's not a fossil fuel because we're not fossils. So a quick detailed analysis. Water is a polar molecule, so two hydrogen and oxygen will be separated by an electric field. The potential energy to overcome the electrolysis, like the bonds, is 1.25 to 1.8 volts. CO2 is a nonpolar, so it will be minimally affected, and the H2 cathode reacts to the CO2 to form CH4. Here's a quick model of our simulation, just an overview. We plan to saturate CO2 into water with an infusing process. And within our prototype, we'll feed that CO2-rich H2O into a series of membranes that have an anode and a cathode made of nickel. And the outputs up top, which is oxygen, and then out the side, which is CH4, with power coming in from that other side as well. So here's a quick mock-up. You can see each individual kind of cell or membrane, so to speak. We input the saturated CO2 H2O in the side, and as it flows through each of those anodes and cathodes, it splits the molecules and recombines to create CH4 out the side, and then the oxygen escapes out the top. Here's a quick, if you take one of these orange cells and flip it on its side, here's a quick cross section. You can see how we've planned to trap the oxygen so it escapes out the top, and then pass any hydrogen through that's created to combine to make methane throughout the system.
Yeah. So I guess the core principle that's really innovative about the process here, the Sabatier process, that is what we're using, has been around for a long time. This is what's called an in situ process, meaning typically you'd have to separate hydrogen separately and then feed it in. What we're doing here is actually creating hydrogen and methane simultaneously. Which has also been done sort of in separate steps. Typically, there's a very expensive fuel cell that's running backwards, that's feeding hydrogen into a bed of packed nickel. But sort of core innovation here with us is that these charged nickel grids are allowing us to, we're able to use them to split the hydrogen into split the water into oxygen and hydrogen, and then immediately have the hydrogen react with the methane with the CO2 to form methane. So the whole process can be done very compact and with very, very small material cost, allowing an individual model to be very low investment to potentially be done at a home level. This is just a quick mock-up because we did do a demo, which we're going to show some videos of, which you can see before you. This is just an outline of what materials went into the demo. Next slide. And here's a little materials cost. It cost us, what was our end? Or I think that end cost needs to be updated, doesn't it? Or
yeah, that end cost doesn't need to be updated.
Yeah,
we have the correct number
$150
later on.
Yeah. Total cost was around $100 for the demo. A little bit more. Here is some photos of the anodes and cathodes that are in there. Like he was describing in the mock-up, you can see there's a membrane in the middle, and then that separates the oxygen and hydrogen so they can't immediately recombine. And then the oxygen comes out one end, the hydrogen is allowed to flow from cell to cell. And then there's attachment points for the two nickel grids. Here's everything kind of soldered together before we slid it into the tube, grind to really shut the solder down. So we put all the cells together and then epoxy them and then slid them into this tube and then drilled some vent holes for the oxygen to come out. So what we're going to show here is a video of our actual demo. Essentially, we had, because to make this a truly closed cycle, we would need to be extracting CO2 from the air locally, or at least having it brought in from a source that's atmosphere to begin with. And then, but for the purpose of our demo, we just kept it simple. We just got one of these home soda makers that's compressed. There's with 8-gram cartridges of CO2. And then that flows through this tube. The nickel anode cathodes are in here. And then there was a power supply, which we're not going to hook up here. And then our initial idea was that methane is not miscible with water, but we weren't really sure how quickly it would escape, if it would be carried away with the water as bubbles, or if it would come out immediately. So we have vent holes here that were for oxygen, but we also measured for methane there, but we also had a catchment because we had to put the water somewhere anyways, where we also looked for signs of methane.
Okay, let's see if this plays. I don't know if we'll get audio feedback.
Can we turn the lights off?
Yeah.
Yeah. Go ahead, you turn off. I think it's number 1.
So I'm going to mute this. I'm going to mute the mic and then play the video with your sound.
Yeah, that's a good idea.
Where the power output was essentially sufficient to produce the reaction.
All right. And I'm going to mute this again.
So we didn't expect, but now we know, actually, the methane does come out of the holes in the top. So if we're redesigning this for a production scale model, maybe a better way to do it would be to actually have the CO2 water recirculating. So maybe have some fresh CO2 going in, but also have it recirculating for high efficiency. Going through the tube repeatedly, so more CO2 is consumed. What?
Methane is heavier than oxygen.
Yeah, and then so have something like a mini still to allow the methane to sink while the oxygen rises out of these vent holes would be the way to do this in an usable product. So from there, I mean, the next thing to do hypothetically would be to try to calculate the efficiency of the process. In the perfect conventional understanding of the Sabatier process, you see the perfect conversion. That's what chemical process would look like. As far as the molar ratios, we have 4 moles of water combining with 1 mole CO2, and then out of it you would get 1 mole of of methane, and the hydrogen and oxygen. Some portion of it would recombine. Actual process, we really don't know how much really came out. There's the potential, some of it beyond just methane and recombined water that could come out. You could have some of the hydrogen that didn't react with the water, with the carbon dioxide. You could have waste oxygen that's coming out, and you could even have, this is supposed to just be carbon monoxide, but so there's a potential that you could have an incomplete reaction. So in terms of the chemical conversion efficiency, you have the moles of methane that come out compared to the moles of CO2, where 1-to-1 is perfect efficiency, and N over C, which is our potential efficiency. We know that what we input was 8 grams of CO2. This was within our budget. This is a combustible gas detector for gas leaks. It goes from 1 to 6. I think Brad put it as like 1 to 6 methanes.
We don't know.
So we really don't know. We know that this can measure into the parts per million range, but we don't have budget mostly to get a actual unit measure. But let's say we knew what it was. We'd get chemical conversion efficiency, and then as far as energy efficiency for a completed process, we have useful energy versus the total input. The useful energy is the chemical energy associated with the methane. So we've got how much methane, how many moles of methane did we get out, mass of molar mass of methane, and then the energy methane, and then that would be over power supply and any other energy inputs, including in a completed process, the extraction process for the CO2. So we know the total energy for our successful run. It took 25 watts. We could possibly have dialed that down lower, but I was out of CO2 charger. And then we know, so basically we have 16 grams per mole times 55 kilojoules per gram over whatever the energy cost of CO2 plus the electrical costs.
All right, so here's the actual cost of our prototype. Earlier, the number was wrong. This hardware approximately costs $116 is kind of what we estimate. The nickel mesh was the most expensive, and you have to buy that in bulk, but cutting it up and recalculating that cost, this is what it is approximately per unit. Again, like in the video, it outputted 25 watts. That was inaccurate what he said in the video of 5 watts. It's actually 25 watts. And the cost, electricity cost of that is about $0.0027 per hour. Let's see, got to hurry through this. So here's our comparison of energy density. We've shown this almost every presentation so far, but 1 gallon of gas is our goal cost to try to get around that cost so we can get an energy or a green energy for around the same cost as a gallon of gasoline. So energy density wise, 1 kilogram of hydrogen is the same as 1 gallon of gasoline. And 2.54 kilograms of methane is approximately that same energy density. Let's see, I'll skip that. The conversion cost is about $1.32 per kilogram. Let's see.
Okay, to be fair, we should stop.
Yeah.
That was very good, very impressive. We have a whole bunch of questions, but I think we should move on.
Yeah.
Very, very cool.